In this video, I'm going to solve every question from the UKMT Junior Olympiad from 2025. That's one of the follow-on rounds to the Junior Maths Challenge, usually taken by students aged 11 to 13, but often also taken by younger students as well. If you're preparing for the Olympiad, you'll want to click the link below and take a look at my free course, Get Ready for the Junior Olympiad, where you can also practice these questions and more with video hints as well as the solutions for the best chance of getting the answer by yourself. It's a really great way to prepare for the Junior Olympiad. The Mathsaurus Courses website also has lots more content to help you prepare for maths challenges and Olympiads and for school maths, so I really hope I'll see you over there after you've watched this video. In question 1, we have a diagram with 3 squares. The larger white square has side length A centimeters and the smaller white square has side length B centimeters, where A and B are both integers. The shaded area is 286 square centimeters. We need to find one possible value of A, then another possible value of A, and then prove that no others are possible. Really, these are 3 parts of one linked problem, and once we find all the possibilities and show there are no others, we've answered the whole question. But because this is question 1 of the Junior Olympiad here, they're just spelling it out a little bit more for us, how many marks there are for each part. But they don't usually do that, it's usually just 10 marks for each question. So, each shaded region is an A by B rectangle, so each one has area A times B, which we write as AB. That means that the total shaded area is 2AB, so we have the equation 2AB equals 286. Dividing by 2 gives AB equals 143. And in number problems, where the answers are whole numbers, finding the prime factorization of this key number 143 here, doing that is going to be a key step. So because A and B are integers, we just look for these integer factor pairs of 143, and 143 has a prime factorization of 11 times 13, and if you didn't spot that immediately, you could just check whether prime numbers are factors up until you find one that works, and we do get 11 times 13. So one possibility is clearly that A is 13 and B equals 11, and that would give us the answer to the first part of the question, and because B is the smaller side length, we can't just swap them around to get a second one. So the other possibility that you need to find here is that we could have A as 143 and B equals 1. So that gives us the 2 answers for parts A and B. And if you just write those down clearly, you're getting the marks for A and B. To get the marks for part C, you would need to write out the argument as we have done here. So you could just get parts A and B by trial and error, but that doesn't prove that there are no other possibilities. So part C is for the write-up, and for most Olympiad questions, the whole of the question is the write-up. So this one is actually quite unusual, giving you marks for the answers in parts A and B. So let's give that concise full answer in part C. What would we write? We would say we know that A, B equals 143, so A and B must form a factor pair of 143. Of course, you'll have the previous working getting to that equation there as well, and explaining why that equation is as it is. The prime factorization of 143 is 11 times 13, so the only positive factor pairs are 1 and 143, or 11 and 13. Since A is larger than B, the only possibilities are A is 143 with B equals 1, or A equals 13 with B equals 11. Therefore, A equals 143 or A equals 13, and there can be no other possibilities. And that gives a nice clear written answer. It doesn't have to be a long answer, it just needs to be complete. So if you use any algebra, we introduce it at the start. Of course, here A and B are given to us in the question, but I would still write a sentence about how that corresponds to the areas. And if you write something like we've done here, you can get full marks. And actually, ideally, a concise answer is better than a long one, so long as it really does clearly include everything that the proof requires. The code for my bank card is a 4-digit integer. No digit is 0. The first digit is twice the third digit. The fourth digit is 3 times the second digit, and the whole number is a multiple of 9. We need to find the code and explain why no other solution is possible. And even if that hadn't been written explicitly here in an Olympiad question, that explaining why no other solution is possible would always be a part of the question. So you might begin by naming the digits A, B, C, and D, and you could do that. Introducing something algebraic is certainly the right instinct. We could also just build in these digit conditions straight away by saying that because the first digit is double the third and the fourth digit is 3 times the second, we could write them as 2A, B, A, and 3B, and this is better than starting with 4 different variables. We've only got 2 to find here, the A and the B. So next we'd want to use the divisibility by 9 condition, and we would write in our answer that we understand that by writing something like, if the number is a multiple of 9, then its digit sum must also be a multiple of 9. So 2a plus b plus a plus 3b is a multiple of 9, which means 3a plus 4b is a multiple of 9. In particular, that would also mean that 3a plus 4b must be a multiple of 3, and we want to use a multiple of 3 here initially rather than 9, because we can see that 3a itself is always a multiple of 3. So it actually tells us something about b, because if 3a plus 4b is a multiple of 3 and 3a is a multiple of 3, then that would mean that 4b would have to be a multiple of 3 as well. And because 4 and 3 have no factors in common, that means that b itself is also a multiple of 3. So because b is not 0, the only possibilities for a digit that's a multiple of 3 would be 3, 6, or 9. But the fourth digit in the number has to be 3b, and that also has to be a digit. So if b was 6, then 3b would be 18, which is impossible, and if b were 9, then 3b would be 27, which is impossible as well. So we must have that b is 3, and so we then also know that the fourth digit, 3b, is 9. So if we can just go back to find a, we can work out the full code. So if we substitute b equals 3 into 3a plus 4b, we get 3a plus 12. And we know we need this to be a multiple of 9. So a has to be greater than 0, so we want 3a plus 12 to be a multiple of 9 that's bigger than 12, so it must be 18, 27, or 36, and so on. Now, if 3a plus 12 equals 18, then 3a equals 6 and a equals 2, which works. But if 3a plus 12 were 27, then a would be 5, and the first digit 2a would be 10, which is too big to be a digit. And similarly, any larger multiple of 3 makes that problem even worse, and 2a will not be a digit. So it must be that a is 2, and then that first digit 2a is 4, and so we have come to the conclusion that the code is 4329, and because we ruled out every other possibility along the way when choosing b and then when choosing a, as long as we've set that working out clearly, we've also explained why no other solution is possible. Here we have a geometry problem on a semicircle. O is the centre, AB is a chord, OC is perpendicular to AB, and angle OAB is 20 degrees. We need to find angle BAC, and as this is an Olympiad problem, we also need to justify the answer clearly, so I will put the key working on the screen as we go through as well. So a good first move here is to draw this line AC, because that is the angle that we're being asked about. It's also helpful to name the point where AB and OC intersect, so let's let that point be M. In a full written solution, you would say that M is the point of intersection of AB and OC. Having the diagram labelled in your solution as well also makes the argument you're making a lot clearer. So I would very much encourage you to include diagrams in your solutions. Because OC is perpendicular to AB, angle OMA is 90 degrees. Also, angle OAM is 20 degrees because M lies on AB. So in triangle AMO, the third angle is 180 minus 90 minus 20, which gives 70 degrees. Since O, M, and C are on the same straight line, that tells us that angle AOC is also 70 degrees. Now, we need to spot here the key isosceles triangle. OA equals OC because they are both radii, or radiuses if you like, of the circle. So triangle AOC is isosceles, which means the two base angles are equal. Spotting isosceles and equilateral triangles in these sorts of questions is a really important skill, and if you've got a circle in the problem as well, radii are very often going to be the thing that gives you isosceles triangles. So those two equal angles add up to 180 minus 70, which is 110 degrees, so each of them is 55 degrees. Now, angle BAC is the difference between angle OAC, which is 55 degrees, and angle OAB, which is 20 degrees, so that means that angle BAC is 55 minus 20, which gives 35 degrees, and that's the final answer. But in an Olympiad question, of course, most of the credit is in the working that you've used to justify it. We need to find all values of a such that a plus 6, a plus 12, a plus 18, and a plus 24 are all prime. Because this is an Olympiad problem, we must also show why no other values of a are possible, and in fact, even if that weren't written explicitly, it would always still be implied in an Olympiad problem that that's what we need to do. So if you don't immediately know how to solve this, a sensible first step is just to play around with a few values and see what happens. So for example, if a is 2, the other numbers are 8, 14, 20, and 26. So that clearly fails because they're even. If we try a equals 3, we get 3, 9, 15, 21, and 27. So that fails because of the multiples of 3 there. If a is 5, the list is 5, 11, 17, 23, and 29. All of those ones actually are prime. So we've fairly quickly found something that can work. But that's really just the beginning of this problem. The real work is deciding whether there are any other possibilities that can work as well. And if we try a few more, it does suggest a pattern. If we do a equals 7, one of the terms is 25. For a is 11, one of the terms is 35. For a is 13, one of the terms is 25 again. And so even in the earlier failed examples we had, we did also have 20 and 15 appearing. So there could be several reasons a list fails, but it does seem to be that multiples of 5 keep appearing. So this isn't a proof yet, but it is a good clue, and it tells us what to investigate next. So let's think about these extra amounts, 0, 6, 12, 18, and 24, in terms of what happens when we divide them by 5. They leave remainders of 0, 1, 2, 3, and 4, respectively, when we divide them by 5. So among the 5 terms in the list, we get all 5 possible remainders when dividing by 5. That means that whatever remainder a has, one of the 5 numbers must be a multiple of 5. So just as even and odd numbers can be written as 2n or 2n plus 1, every integer can be written as one of 5n, 5n plus 1, 5n plus 2, 5n plus 3, or 5n plus 4. So if a is 5n, then a itself is a multiple of 5, so the only prime possibility is a equals 5, and that's the case that we've already found. If a is 5n plus 1, then a plus 24 is 5n plus 25, that's 5 lots of n plus 5, so it's a multiple of 5. If a is 5n plus 2, then a plus 18 is 5n plus 20, which is 5 lots of n plus 4, so that one's a multiple of 5. If a is 5n plus 3, then a plus 12 is 5n plus 15, which is 5 times n plus 3, and so that one will be a multiple of 5. And if a is 5n plus 4, then a plus 6 will be 5n plus 10, that will be 5 lots of n plus 2, so that one would be a multiple of 5. So every form except that special case, a equals 5, does turn out to be impossible. Finally, we can just check that one surviving value that we already have done here, but that's how I'd write it up in my argument. I would prove all these cases are impossible apart from this one where a equals 5, and all that remains is to check that the other numbers are prime and they don't end up being not prime for some other reason, not to do with being a multiple of 5, but we get that list 5, 11, 17, 23, and 29, and all 5 of those are prime, so that means the only possible value is a equals 5, and if we've written our working out in the way that I've explained it here, then we have at the same time also really shown that nothing else can work. For which values of n with n at least 3 can you make an n-sided polygon by joining several 1x1 squares together edge to edge? The diagram in this question shows an example of an 8-sided polygon made in this way, so be careful here. The example we're given, it's not a tile that we're trying to make lots of copies of that tile. That is just one 8-sided polygon, that T-shape, that is an example of what we get by forming a polygon by joining squares together. Again, because this is an Olympiad problem, we have to show 2 things: that every value we claim is possible really can be made, and that no other values are possible. So if you play around with some examples, that's always a good way to start this sort of question. Just try to convince yourself what the answer is meant to be before you try to prove it. What you will find is that you can do it for even numbers greater than or equal to 4, but not for anything else. Now, let's think about why that is and how we would prove that. So the lower bound of 4 is quite natural, of course, because any such polygon has at least a left side and a right side and at least a top side and a bottom side, so it has to have at least 4 sides. So the proof from there has 2 main parts. We need to find some way of showing that we can make a polygon with 4 sides, with 6 sides, with 8 sides, with 10 sides, and so on, but do it in a way that we show that all of the larger values are possible as well, not just examples of smaller values. And secondly, we need to show that odd number of sides can't happen. To show that every even value is possible, the easiest method is to give a clear construction. So if we start with 2 squares next to each other, that gives a rectangle with 4 sides. Now add a square above the second square. if we make an L shape, the result has 6 sides. To continue, add the next square to the right, then the next one above that, and keep alternating right above, right above. Each time we add a square in this zigzag pattern, one existing side is extended and 2 new sides appear, so the number of sides goes up by 2 each time, and that gives us polygons that have 4, 6, 8, 10, 12, 14 and so on sides, and it does then show that if we continue this, every even value of n greater than or equal to 4 is achievable. Now, why are odd values impossible? We need to prove that odd values of n cannot happen. So let's take any polygon made from these unit squares and choose a vertex of the polygon itself. That means a real corner of the outside boundary, not just a corner of one of the small squares. Now travel around the perimeter, the outside boundary of the polygon from side to side until you return to where you started. Every side is either horizontal or vertical, and as you go around the polygon, these types alternate: horizontal, vertical, and so on. The final side before you return to the starting point must be the opposite type from the first side. So the alternating list of sides has to have an even length. Equivalently, there are the same number of horizontal sides as vertical sides, so the total number of sides is twice the number of horizontal sides, and therefore the total number of sides is even. So I'm saying the same thing in 2 different ways that you just need to write one of those 2 things down. So that does show then that any such polygon has at least 4 sides. We've constructed polygons with every even number of sides from 4 upwards, and we've proved that an odd number of sides is impossible. So the possible values are exactly all of the even integers n greater than or equal to 4, and if we write that out clearly and carefully, then that would be a complete answer for an Olympiad question. This question tells us that the sum of the factors of 2025 is odd, and we need to find the smallest number n that's greater than 2025, whose factor sum is also odd. And because this is an Olympiad problem, we must show 2 things: that our value of n works, and that no other smaller value, i.e. between 2025 and n, works. And if you don't immediately spot the idea you need here, which most people will not, because this is an incredibly difficult question, a reasonable first step is just to start testing out a few numbers. For example, let's try 2026, that's 2 times 1013, where 1013 is prime, so its factors are 1, 2, 1013 and 2026, and the sum of those is even, which we can see without working it out. We've got 2 odd numbers and 2 even numbers, it's going to add to give an even number. 2027 is prime, its only factors are 1 and 2027, again the sum is even. This is a good question where actually if you have thought about the prime factorizations of the current year and perhaps even a few future years, you will be helped in this playing around with it. So the important observation here is that even factors really aren't going to affect whether the total sum of the factors is odd or even. It's only the odd factors that matter. And for any number, if we ignore the powers of 2 in its factorization, the odd factors are exactly the factors of the odd part that remains, if that makes sense. So for example, if we look at 2028, it's 2 squared times 3 times 13 squared, and like the odd part of that is 3 times 13 squared, which is 507. But the factors that would have the 2 or the 2 squared in them are just going to give us even factors. So I can just think of the factors of 507 and try to decide if the sum of those factors is even or odd. So the question becomes, when does the odd part have an odd sum of factors? Now factors usually come in pairs. So for 12, for example, the pairs are 1 times 12, 2 times 6, and 3 times 4. But for a square number, one pair sort of collapses into the middle. So for 9, we have 1 times 9 as factors, and then 3 times 3. So the factor 3 is counted only once. And again, this is something that experienced Maths Challenge and Olympiad students might already know in advance, that an odd number of factors occurs exactly when a number is a square number here. So otherwise we get an even number of factors because of those factor pairs. So since all factors of an odd number are odd, an odd number has an odd number, a sum of factors exactly when it is a square number. And for a general number n, let's write it as a power of 2 times an odd number. So the even factors don't affect whether the factor sum is even or odd. So we need that odd part to be a square. Therefore, the numbers we want are powers of 2 multiplied by square numbers. They are the only sorts of numbers that can work here. It's got to be an odd square number multiplied by 2 or 2 squared or 2 cubed or 2 to the 4. But this simplifies even more, because if the power of 2 itself is 2 to an even number, then the whole number is square again. So actually, if the power of 2 is odd, the whole number is twice a square. If the power of 2 is even, then it's exactly a square number. So the numbers we're looking for actually are the ones that have this odd factor sum, are exactly when it's either a square number itself or when it's twice a square number. So we've really reduced what we're looking for here to something a little bit easier. Very, very difficult question. So 2025 is 45 squared, and that's why it gave us this odd sum of factors, because it is a square number. Now the next actual square number will be 46 squared, which is 2116. So all we need to do now is to check whether there's something in between, which is of the form 2 times a square number, because that could also work. And if we start searching, we want to just try and get something close to 2000 here. So say 31 squared times 2, we can work out as 1922. Just keep searching until you get something close to 2000. And 2 times 32 squared, that's 2048. So that one actually is bigger than 2025 and smaller than 2116. So 2048 is less than 2116, and so that is the smallest value that we can use there. And it was important that I had 2 times 31 squared in my working as well, right? Because I'm showing here that the one before 2 times 32 squared doesn't work, and that 2 times 32 squared is the first one that does work. So the final answer then is that 2048 does work. It's 2 times 32 squared, which is actually in itself a power of 2 as well, 2 to the power of 11. So its factors are powers of 2, and actually the only odd factor it's got is 1, which again, you potentially could have spotted, I suppose. You could have said, oh, for a power of 2, the only odd factor is 1, and that one does work, and the sum. But if you were to give that working, you would also need to have some very clear working about why nothing between 2025 and 2048 worked. In theory, you could do that exhaustively, I suppose, by writing them all out. We've only got 20 or so to do at that point, but it would be a lot of work. And the way that I've explained it here is definitely a more elegant mathematical solution to the problem. But any correct logic, so long as it is fully explained and rigorous, would get you the marks here. So we've proved the only possible numbers are squares or twice squares. We've checked that the next squares and double squares after 2025 are what they were. 2048 is the smaller of them, and so the answer to this question is that n equals 2048, and very well done if you got anywhere near the answer to that one. And if you're still here at the end, firstly, well done for getting this far. Secondly, don't forget to check out the Mathsaurus website, where there's loads more free content. You can practice for maths challenges, Olympiads, and more, or you can take a look at the video on the screen now and work through another full paper with me here.